Remember, we are working with probability distributions, and this is about the binomial distribution. A binomial random variable counts the number of successes, when something is repeated n times. And there are four conditions of a binomial experiment. The first one is the experiment is repeated a fixed number of trials. So the experiment is repeated a fixed number n of trials. The second condition is the trials are independent. The trials are independent. And the third is each trial has two outcomes. Each trial has two outcomes. Success or failure. And the last one is that the probability of success, remains the same stays the same on every trial. On every trial. So those are the four conditions to have a binomial experiment. Next, we discuss the notation that we are using for binomial probability distribution. So n stands for the fixed number of trials, for the fixed number of trials. P stands for the probability of success in one trial. And Q stands for the probability of failure, the probability of failure in each trial, or in one trial. And then X stands for number of successes. The number of successes in n trials. In n trials. So in other words, x is any whole number, x is any whole number between 0 and 1. Zero and n, rather, 0 and n. Let's look at some examples. Which of the following are binomial experiments? If not, explain why not. A player rolls a pair of fair dice 10 times. The number x of sevens rolled is recorded. So we know that 10 trials to n equals 10. So that's a fixed number. Each roll is independent. Each roll is independent. Then there are only two possible outcomes. Two outcomes. It's a 7, or not a 7. And the probability is fixed. The probability is fixed. In other words, it's the same on each roll. The same on each roll. Okay, the next one says the 11 largest airlines had an on-time percentage of 84.7% in November of 2001, according to Air Travel Consumer Report. In order to assess reasons for delays, an official with the FAA randomly selects flight until she finds 10 that are not on time. The number of flights X that need to be selected is recorded. Well, until she finds 10 that were not on time, so in other words, n is not fixed. N is not fixed. So it is not a binomial distribution, not a binomial. Let's look at a third example. When an adult is randomly selected, there's a 0.85 probability that this person knows what Twitter is. Suppose we want to find the probability that exactly 3 or 5 randomly selected adults know of Twitter. Does this procedure result in a binomial distribution? Well, let's see. Is the number of trials fixed? Yes, there are 5. N equals 5, 3 out of 5. So n equals 5. And each pick is from a large population. We can treat each trial or each pick as an independent. So each pick is from a large population, which means we can treat each pick as independent. So we go to the independent part, independent And then the two outcomes. Two outcomes possible. And the two outcomes are, they either know what Twitter is or they don't. Knows Twitter. Or does not. Not know Twitter. And last but not least, the probability of 0.85 is fixed. Is fixed. So we can conclude that this will result in a binomial distribution. So you just have to evaluate the given facts against the four requirements for a distribution to be a binomial experiment. 1, 2, 3, 4, as we had before. Here's another example, basketball example. I'm not great at basketball. I make about 25% of my shots. I plan to take 2 shots and let X be the number of baskets I make successfully. Is this a binomial experiment? So we check all 4 conditions. Well, there are 2 triads, so the number of triads are fixed. There are n equals 2 triads. Second, each shot is independent. Third, there are 2 outcomes. I make the shot. I make the shot. Or I miss. And fourth, the probability is the same. The probability of success is the same, 25%. Success chance of success remains the same, is the same. Okay, so what are the values for n and p? Well, we've already said that n equals 2 and p is 0.25. Now, we haven't really talked about failure here, what the chance of failure is, but q would be simply q is equal to 1 minus p, because we know that success plus failure has equal 1. So q would be then 0.75. And the next question is, what are the possible values of our random variable x, the number of successful baskets that I make out of 2 tries? What can happen? Well, you can miss both, so then x equals 0, no success. Or you can make 1, or you can make 2. So let's look at what this looks like in terms of a probability distribution. So our random variable is, x could be 1, 0 is 1, 0, or 2. Now the probability, for the probability we need to determine what that is. So to visualize how to set up the probabilities, we use a tree diagram. So let's say we start out with a failure. The probability of missing two shots is 0.75 to the second power, because the probability of failure is 0.75. So that equals 0.5625. Then let's say we have a failure here, and here we have success. So now we have the probability of failure success would be 0.25 times 0.75, 0.25 times 0.75, or equals to 0.1875, 1875. Then on the other side, here we have success, and the probability of success, another success, is equal to probability of two consecutive successes is 0.25 to the second power, which is 0.0625. So that would be here. And then the probability of a success and a failure here. So the probability of a success and failure, of course, is equal to 0.75 times 0.25. And of course, it's also equal to 0.1875. So we add these two together, and we get 0.375, where we have one failure and one success, or one success and one failure. Of course, the product is the same, so we multiply 0.1875 times 2. And then for the probability of two failures, we have 0.5625, 0.5625, and the probability of two successes was 0.0625, so it goes in here, 0.0625, and this adds up to 1.00, so that works. So to summarize it then, the probability that I make 0 shots out of 2 is 0.5625. The probability I make 1 shot out of 2 is equal to 0.375, and the probability to make 2 shots out of 2 is 0.625. Okay? So in a similar way, let's say we are a little bit more ambitious now, and we look at X as the number of successful baskets out of 5 trials, so N equals 5, P equals 25, the numbers of successes on each one, so that remains the same. And when we work out the numbers, so here, to make 0 shots out of 5 would be the probability of 5 successive failures. And because the trials are independent, this, the probability of one failure is 0.75, would be 0.75 times to the 5th power, and that is equal to 0.009765. So there would be the probability here. I'm sorry, this 0.2373. So I looked at the wrong results here. So that's 0.2375. So 0.2375. And then going to the last one here, I make 5 successful shots. It would be the probability of 5 successes, and that's equal to 0.25, again the independent events, so we raise that to the 5th power, and that is equal to 0.0009765. So 0.00, well, we can just make it 0.010, 0.0010. Now the probability of making one shot out of 5, there are 5 different ways that can happen. It could be success, failure, 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 and it could be failure, success, failure, 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 etc. And so, as you can see, of course, the product is always the same, and so, but it could get very complicated. That's just for this one here. And so it's really better to use a formula for this, and that is really what we're going to look at next. So here is the binomial formula, which we'll be using many times in the future. And it's basically the number of possible orderings, the number of possible orderings, like we did a moment ago in the other example with 5 shots, times the probability of success raised to the number of successes, times, these are all multiplication, times the probability of failure, raised to the number of failures. And the symbol divided as the number of n combination taking x at a time times the probability of success raised to the x power times q raised to n minus x, which would be the number of failures. So this symbol here stands for the possible combinations of x successes and n trials. The possible combinations, possible combination of x successes in n trials. Okay, so with that formula, so now let's use this formula to compute the probability of one success out of 5 shots. So it would be the combination of one success out of 5 shots times the probability of success is 0.25 raised to the first power because it's one success, and then 0.75 is the probability of failure to the 5 minus 1 power or fourth power, and that is equal to 0.3955. 0.3955. So it'd be here, 0.3955. So what I want to explain to you real quick here, what it means, the combination of one success out of 5 trials. That's equal to 5 factorial divided by 5 minus 1 factorial times 1 factorial. So it'd be 5 times 4 times 3 times 2 times 1 divided by 5 minus 1 would be 4 factorial. So 4 factorial is 4 times 3 times 2 times 1. And then 1 factorial, of course, is simply 1. So that these numbers cancel, so that's equal to 5. You cancel 4 against the 4, the 3 against the 3, the 2 against the 2, and the 1 against the 1. I will do one more entry for you, and that's a probability of exactly 3 successes. So it'd be the number of 3 successes out of 5 trials times the number of successes to the 3rd power times the number of failures, times the probability of failure to the 5 minus 3 or to the 2nd power, and that is 0.0879. So it's 0.879. And I leave the rest of these numbers up to you as an exercise. I will fill in the numbers for you so that you know you're on the right track. So when you do the same calculations as I indicated here for the probability of exactly 2 successes, do it 3 successes, do it for the number of 2 successes, and you should get 0.2637. And for the exact number of 4 successes, you should get 0.0146. 0.0146. And of course, it all adds up to 1. And so you have all these probabilities. And when you draw a probability histogram, it looks like this. And we've seen that before. We know how to construct that. And it turns out that the mean in this particular case, well, let's talk about the mean for the binomial distribution. With the probability distribution the way it is now, we can compute using the previous formulas for the mean, the sum of the random variable times its expected probability. And so we can do that, and it comes out to 1.25 if we use that. And for the standard deviation, the formula was a little bit more complex. Let me write it out here. We can see if we can squeeze it in. It was the square root of the sum of the random variable squared, x squared, times its associated probability, minus the mean squared. There was the standard deviation. And when you apply this formula, your answer will be for the standard deviation 0.9682. Now, fortunately, there's a much easier formula for the mean and standard deviation for binomial variables. And so, it turns out that the mean of a binomial random variable is simply the product of n times p, the probability of success. And the standard deviation is the square root of n, the number of trials, times p, the probability of success, times q, the probability of failure. So that applies for binomial random variables. So there we go. Okay, so the mean is equal to the number of trials times the probability of success, and the standard deviation for a binomial random variable is the square root of n times p times q, where q is the probability of failure.